Hey, what's going on, everyone? Just getting things going. It's gonna take me a couple minutes to just get it all set up. I need to create a new. I think I have active accounts for this game because I have played it in the past, but I have not finished it ever. So we're gonna hopefully try to finish it today. Not today necessarily, but this time starting it. Um, if you don't know what microcorruption is, let me get out of the inception real quick. Microcorruption. This is a embedded CTF where everything is virtualized. So it's hardware based. So all the examples are like this lock thing where you get to provide some input and and then do some kind of exploitation that causes you to get code execution. And once you have code execution, you can do other cool things. So let me go back to the webcam real quick and let me see which accounts I have on here and what they are, how far into the game they are. I think we're going to start from scratch, but I don't know if it makes sense to just like make a new account, or can we resolve these or not? It looks like we can. Yeah, okay. It looks like we can resolve them. I think we'll just, well, I don't know. Maybe we'll make a new one. Let's go ahead and do that. And I'm gonna do this off screen real quick, just because I don't want to leak anything potentially sensitive. And I want some like quick technical details here about me. I literally just want an account. This is so stupid. Yeah. This is all optional stuff. I'm an infosec person. I don't know. Say that I've got like 10 years experience. Working email address. All right. So they should be sending me an email in a few minutes or seconds, some period of time. And this will let me go and create an account. All right. All right. I don't want to update. I want to create a new one. All right. So we are in the game now. So this is what you get to when you log in. Basically, there's all these different little places around the world, and you click one, and that's like a challenge. I know what I'm doing. Just let me go. Yeah. So I don't really care. Basically, this is all based on MSP 430, which is an embedded architecture. It's made by TI. It's just like a microcontrollers, like ISA, and it is, I believe, a RISC architecture, but I'm not 100% sure on that. But basically, we have our register state up here. program counter, stack pointer. I don't know what SR is. I don't know what CG is. These are, I believe, just general purpose registers. This tells you what your current instruction is. This is our debugger console, so we can interact with it, and it lets us do things like set breakpoints and inspect memory. It's, I think, somewhat like GDB. This is I/O. This is our memory, and I don't think this separates out like the different. I mean, I think it's just like all put together. So like your stack, there probably isn't a heap on here. Program memory itself, like there's no segmentation of memory here. And then this is our disassembly of the firmware that we're running. There's a few things that we're going to need. We're probably going to need the lock manual. This gives us details about the just like documentation about the war game. We're probably going to want a ISA document that kind of walks us through like the architecture, so that we can see effectively like how the instructions are encoded, because we're going to have to like write our own I don't want to say like machine code, but like our own assembly basically. But they give you access to an assembler here. I don't know how good it is, and like theoretically like we could write our assembly here, and I don't know, I think ret is probably an instruction, and it'll spit out the machine code for us here, hex encoded, and so like I think we can just use this to input. I think last time I was working on this, I literally did it all by hand and didn't use this. I don't know if it existed at the time or if I just didn't realize it was there. But it was really frustrating having to go and figure out like, okay, yeah, like a move instruction is like, I don't know, like 20, and then the arguments are encoded this way, and having to do it all manually. But it was cool. It was a good experience, and it was fun. I think I've gotten about halfway through the game ever, and I don't really remember like anything about it. So I'm probably going to be just as stumbly through it as I was the first. I think this is the third time I've started it. So, but we'll see how it goes. 1 second. So, we have the manual, we have the assembler, and we have this. We need to figure out what our goal is. Connected over JTAG. Use this mode to figure out what the lock is doing, and then leave the debugger upper left button. I don't know where the upper left button is. Is it this? No. That doesn't help us. I think we type solve, and that does it. Yeah, leave it. Let me see if I can go back into this and see. We'll kill it that was running. Yep. All right. Let's just go through this. Scattered throughout the world in locked warehouses and briefcases filled with Psi Combinator or Psi Yombinator bearer bonds that could be worth billions, billions of dollars. You will help steal the briefcases. Psi Yombinator has cleverly protected the warehouse with locktail electronic devices. Locktail locks, lock it all. Locks are unlockable with an app. We've positioned operatives near each warehouse. Each is waiting for you to successfully unlock the warehouse by tricking the locks. The The Lock It All devices work by accepting Bluetooth connections from the Lock It All Lock It Pro app. We've done the hard work for you. We spent $15,000 on a development kit that includes remote-controlled locks for you to practice on and reverse-engineered enough to build a primitive debugger. Using the debugger, you'll be able to single step through the lock code, set breakpoints, and examine memory on your own test instances of the lock. You'll use the debugger to find an input that unlocks the test locks, then replay it on the real lock. Cool. Yeah. Memory viewer, like we already said. Did this already, I believe. Can see up. Yep. All right. It wants us to enter the password. Okay. This is the IO console. Oops. CPU input goes here. All right. We're gonna reset. Step through the CPU, see what's going on, type reset. Breakpoints, all right. Okay. We're gonna single step. All right. This is how they all interact with the user. Request input or do just about anything. So int is interrupt. So I think this is an interrupt handler basically. So we're probably going to be caring about that somewhat. The partial output, the program is shown here. Type continue. All right. We can now step out of the current function by using out. You're not yet at the main level. F. All right. The check password looks interesting. So we can go and look for the check password. And we're going to continue, and this will break there. Yep. All right. This means move whatever is at memory address 15 to R14. Look at the value of R15. I don't know if the ampersand here is like a dereference. Move whatever is at memory address 15. Yeah, so I think that is a dereference, which is interesting that that's the syntax that they use for it. Into 14, look at the value of R15. So we can see R15 here. It's 439C. All right. Okay. The next instruction is to add 1 to R12. Oops. The jump if not 0 instruction is considered a jump, which will move the program counter when the 0 flag is not set. This one jumps back by 8 bytes. So it's jumping 4484. Yep, so this is basically a loop. Mouse over it to look at the flags that are set. C means carry. The result of the last instruction was 0. The 0 flag would be set. It's not though. also unset your other breakpoint with unbreak check password. C. All right. Type S. Come on. Moving. All right. This box lets you enter hex encoded values for when you need to enter characters. For example, that you type 7465. So this is the ASCII value of hex in hex. All right. Wait. All right. So do solve and we type password. All right. So we just walked through like the little tutorial thing there. That seems fine. Let's do the real one. Yep. All right. So user manual, lock it all, lock it pro rev 0 a.01. So this is the first lock it pro lock. This lock is not attached to any hardware security module. So they bring in the idea of like HSMs, which are hardware security modules. These are basically like hardened crypto devices that do crypto operations and store key material, but don't let you take key material out. So they typically will have some kind of tamper evident or anti-tamper hardware on them or like mechanical stuff on them, so that either if it detects tamper, it wipes the keys out, so you end up losing all the data, or it becomes evident that the device was tampered with. So Lockit Pro 8.01 is the first of a new series of locks. It is controlled by an MSP430 microcontroller and is the most advanced MCU-controlled lock available on the market. The MSP430 is a very low-power device which allows the Lockit Pro to run in almost any environment. The Lockit Pro contains a Bluetooth chip, allowing it to communicate with the Lockit Pro app, allowing the Lockit Pro to be accessible from the exterior of the building. There is no default password on Lockit Pro. Upon receiving the Lockit Pro, a new password must be set by connecting it to the Lockit Pro app and entering a password when prompted, and then restarting the Lockit Pro using the red button on the back. This is hardware revision A. It contains the Bluetooth connector built in and one available port to which the Lockit Pro deadbolt should be connected. This is software revision 01. All right, so we need a little bit of reverse engineering here. There's not that much code, so I think we should be able to like do this like pretty easily. Basically, we want to run this code right here. So I'm going to do this backwards. And so what I'm going to do is I'm going to look for whatever calls unlock door. So that's called right here. And we see it's in main. So let's go through main and let's see like how we get to like this code path. This is like one approach you can take to like solving these kinds of problems. So we add FF9C hex to the stack pointer. I think that this is all like what's it called, like AT&T syntax, where the source is on the left and the destination's on the right, rather than like Intel syntax where you have it effectively like swapped, which is the more common one that most people think of when they think of assembly. Yeah, so like we're moving this like the location of this string to R15 here. So create password is called. We can look at what that does. Basically, it is moving this address into R15, and then these all appear to be ASCII. So what I'm guessing is that this is the actual password getting moved into offsets off of R15. So this is the address going to R15, and then the first byte, second byte, third byte, fourth byte, fifth byte, sixth byte, seventh byte, eighth byte, and then this is a null byte, which means it's the end of a string, so it can do a string operation on it. I'm going to pop open WSL so I have like a programming environment that is actually useful to help us around here. So what I'm going to start doing here is I'm just going to convert these into their ASCII representation, and we'll see if using that will just give us the password. I think that it's probably going to. So 61, 58, 59, 67, 42, 62, 69, and 0. We don't really care about that. And we're going to join on empty. So this appears to be the password. We're going to go ahead and just run this and see if this works. Do I have breakpoints set? I must have breakpoints set. So it's asking for password. I'm just going to paste this in. Access granted. Cool. So that worked. So we're going to go ahead and solve this. And we're just going to type the password in. All right. Should we document this? I guess so. Do New Orleans. Let's get our code from here. Create password function. It's called at the beginning of main, which sets the password for the device. This simply moves the password byte by byte into memory. We can pull the individual characters out of the function. Their ASCII representation to get the password. All right. So we solved New Orleans. Let's go to Sydney. All right, so we've revised software in revision 2. This lock is not attached to any hardware security module. So again, no HSM, meaning that there's no crypto. The Lockit Pro A.02 is the first of the new series of locks. It is controlled by an MSP430 microcontroller, and it's the most advanced blah, blah, blah. There's no default password on the Lockit Pro. Upon receiving Lockit Pro, a new password must be set by connecting it to the Lockit Pro app and entering a password when prompted. Then restarting the Lockit Pro app. Okay. So they remove the password from memory. We're going to go to main again. We see that it is... it has the access granted here. It's calling puts. And, oh, we don't want those breakpoints. We're seeing it request a password. It calls puts here, which is printing that string. It's going to check the password and get the password here. Probably want to look at these two, and then basically it's going to test R15. So the return value of check password is going to be in R15. If it is what is this? Jump not 0 to 445E, 445E. So if it is not 0, then it will go to here. So we basically want this to return a non-zero number. Otherwise, it'll fall through and it will say invalid password and jump to 4470, which is down here. I think CLR. This if it's the same instruction in AVR, it clears interrupts, but not sure yet. So this is introducing, I think, interrupts. So push 7F, and then call int. So if we look at int, basically, let's go over here. We want this, software interrupts, I think. Lockit has extended the MSP430 to support software interrupts implemented with a call gate at address 0010 on the microcontroller. When the CPU executes instruction at this address, CPU begins executing special purpose lock. There's like something special here. The door lock. When the Lockit Pro While the Lockit Pro contains the circuitry to function, it does not contain a physical lock. The door must be attached to output pin 7 of the MCU. This enables the CPU to trigger software interrupt 7F to directly trigger the door lock to unlock. The door lock automatically relocks after the door has been opened. No further commands must be sent. So basically, calling interrupt 7F will trigger the door. So that's why here we're seeing it's pushing 7F onto the stack, and then it's calling int. And basically we're just gonna take that that value, and then that's like the interrupt we're gonna fire. So we're probably more interested in the check password function. Let's see what that does first. This also looks like it's just straight up encoded data, but it's doing it like as a 16-bit integer rather than 8-bit integer. Let's check this out real quick. 7, 8. And this is going to be backwards because it's, well, I don't know if this is little endian. We should probably find that out. MSP430 NDNS. MSP is little endian. Okay, so we are going to have to swap these, which means it will be 40, 7, 8, And we see that like they're just indexing it, 0, 2, 4. 2B. Yep, these are still all in the hex, in the range of valid values for ASCII. 7, 3, 4, 6. 7, 6, and 3, 8. Yeah, so I think this is still the password. Let's give this a shot. We'll reset, continue, and try this. Cool, so it unlocked. We're gonna do solve, and there we go. We completed it. So again, pretty simple. Let's document this up. Microcorruption. The password is hard-coded into the firmware. This time in the check password function, moving the individual bytes into memory to compare against as a string. It compares the 16-bit 2-byte values against the password as part of the check. These values can be pulled out and converted into their ASCII representation. Because the MSP 430 is little endian, we need to swap the order of the bits. All right. And then the password is this. Hanoi. So as you go into this, like more and more open up, and you can kind of like choose your own direction. Let's see what Hanoi says. All right. So this one has a HSM on it, and let's see. Yeah. Does this one also have an HSM? It's not attached to a HSM. Well, let's see the first one. I don't know if one's more difficult than the other. This is worth less points, so maybe easier. So we've updated the lock firmware to connect with the hardware security module. It's connected to an HSM1. Still MSP430. I think all these are MSP430. There's no default password. Upon receiving the Lockit Pro, a new password must be set first by connecting to the Lockit Pro HSM to output port 2. Connecting it to the Lockit Pro app and entering a new password, then, when prompted, and restarting Lockit Pro button on the back. HSM1 stores the login password, ensuring users cannot access the password through other means. The Lockit Pro can send the Lockit Pro HSM1 a password, and the HSM will return if the password is correct by setting a flag in memory. This is hardware revision B. It contains a Bluetooth connector built in and 2 available ports. The Lockit Pro deadbolt should be connected to port 1, and the Lockit Pro HSM1 should be connected to port 2. So the HSM is doing our comparison now, so we're not going to see the password itself stored in memory like we have in the first two we did. Big things to call out is that the HSM will set some location in memory, so it's probably doing some kind of DMA or like memory mapped IO or something like that. So once the HSM does the comparison, it will set memory in the chip's memory space. This means that if we need to, we can always set that by overwriting the memory address, and then it will effectively unlock the device. I don't know if we're going to have to, but we can see. Let's look around at the code here and see what it's doing. There's this unlock door function, which basically just does that interrupt. Test password valid. This looks interesting. We've got some strings here. Oh wow, it's confusing. So remember, passwords are between 8 and 16 characters. Good to know. So password's probably big enough that we can't brute force it, and there's not really an easy way for us to like submit that here. So it's probably not the path we need to take. Let's see here. So there's this function getSN. I'm assuming this does a read of some sort. And then we do test password valid. And then we test whether the return value of that is 15. Is 0, and if it is, I think it's the same as before. If it's 0, then it goes to, what is it, +8. So... 1, 2, 3, 4, 5, 6, 8. Yeah, so I think it jumps down. It just jumps over this basically, and goes to the password is valid, and then does all this shit. Otherwise, it moves 8D into the air. Yeah, I'm not sure if this is 8 instructions or 8 bytes ahead, but we'll figure that out in a few minutes. So let's look at two things. One is let's look at this code and see what this is doing, because this probably is going to be somewhat interesting. So 7D, I think, is the HSM. It's gonna basically like do whatever it is to do our check. We can verify that by going to the manual here. So 7D, yeah. The Lock It All Pro includes several hardware security module interfaces along with the Lock It Pro. The first of these is Module 1. The Module 1 of the hardware security module contains a simple interface, which allows the MCU to test if an entered password is valid. By default, the interrupt 7D will pass a given password to the HSM, and it will set a byte in memory if the password entered matches the stored password. The stored password can be reset by detaching the HSM from the lock and attaching it to the Model 1 reset device, also included. This might be interesting. There might be a way for us to do this like virtually and get it to like reset. Don't know yet. But basically 7D will do the interrupt for us, which we see right here. And this is, let's see, so we're pushing R4, we're moving SP into R4, and then incrementing R4, decrementing. So I think this is effectively like the R4 becomes our base pointer, and SP stays our stack pointer. And then this is like just saving our base pointer, and we'll see it gets popped off right here. So R4 is a base pointer. and then this is going 4 bytes below, so like it's the, sorry, this is 4 bytes above where our current stack is. So this is into our stack frame, basically. And I'm not really sure what this is doing yet. I mean, this is the calling convention, so it's pushing these 2 arguments on, and then it's calling the interrupt. But I'm not sure. I assume that one of these is probably the string, and then maybe the other one is a thing to update, like an address to update. FFFC, is that even? Yeah, I don't know what that is. So probably not super interesting to us. There's a very good chance that there's just a Stack Overflow here. This getSN function, this is what we saw getting called. So it pushes R14, it pushes R15, and it pushes 2. And then it calls int. So this is the interrupt right here, 2, and I don't know what 14, 15 are. We can see what is moved into there. So 1C is moved into R14. That seems like a size, and it's probably like 16 or something. So 1C, hex 28. And then this looks like an address, maybe. Yeah, so this gets passed into the test password valid. So let's see here. If this is an address, maybe we can set a breakpoint there. We can run it. Yeah, so this is memory here. So then we can next. All right. So yeah, this is where it gets written to right here. We see that this is written into our. This is, I don't know what data this is. It's what segment it is, but it's somewhere in memory. We're gonna call F for finish, and we're gonna finish to get back out of here. It's weird that there's this get char function, but I don't know if it's being used. I don't see it being used. Yeah, it's just not used anywhere. All right. So it looks like we're gonna run this. Step, finish. We're gonna test R15. R15 is 0, so it means we're gonna jump. Oops. Step. We're gonna jump forward 8 hex. I don't know if it's 8 bytes or 8 instructions, so let's see. It looks like it's 8 bytes. So it's telling us that it's going to test if the password is valid. What is this? Move 8D into 2410. Okay. So I think that we can end up just doing this. We skipped over this step, but we can probably just write past here and put the 8D there. So step, finish, and so there's FE and there's the other value 8D there. Jump not equal to FE. So all right. So we were here. Sorry, we want to keep that and we want to keep this. So we're going to compare the byte FE with what's at the address 2410. And we see clearly that like we can probably write past here. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So these are our 16 bytes that are supposed to be our password. But we saw before that we can write up to I think 28 bytes. So we can go past that into here. And so we can... If the value is FE, jump not equal. I mean, it's not equal. So let's put the 8D in there first. We're gonna restart. So we know we need 16 bytes and then our 8D. Reset. Continue. We can skip that. All right, so 1, 2, 3, 4, 5, 6. Oh, you know what? We're gonna do hex encoded because we gotta do this because it's not printable. A is 61. Well, we'll just do capital A. It's 42. 41. Wow, not recognizing that. That's so 41. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and then we're gonna need to do 8D. I'm gonna copy this so we don't lose it. Finish and finish. And we're gonna continue. Continue. Password is not correct. Can you do the FE? Sorry. Are there 2 bytes? Those are the same addresses, right? 2410. Step, finish. Step. Okay, so yeah, that worked. All right, so we're ready to solve, and FE. So the trick here is there is a buffer overflow in the what function was that? It's not login. It's is it login? It is login. Login function. 1C characters. Between 8 and 16 characters. This allows us to overwrite the memory address hex 2410. FE. Store there if password is correct. All right, we did Hanoi. I don't know who all is on here right now, but have anyone played this before and actually like gotten through all the challenges? I'm not sure how many there are. I think there's something like 15 or 16. Maybe more. So this popped in before Reykjavik was the one that had no HSM on it. We can go back and do this one. Well, let's see. How many points is this worth? This is 25. This is 35. I wonder if these are just exploitation route and the other ones aren't, like Reykjavik isn't. So basically, they fixed the buffer overflow, I think, here. Let's go back into here. We fixed issues with passwords, which may be too long. This is attached to HSM1. There's no default password. Taint with detector. This is software revision 2. We have improved the security of the lock by removing a conditional flag that could accidentally get set by passwords that were too long. So let's see how this actually works. So we are moving in hex 30, which is 1632 48. So it's 40. It allows 48 bytes of data to get read. and it's writing it directly onto the stack. So it's very likely that this is just going to be a straight up Stack Overflow, and that we are going to be able to redirect control flow to unlock door. If I had to guess, that's what I would. That's what I'd be guessing is what we have to do. We can verify this by setting a breakpoint here and resetting continue. All right. So our stack pointer is 43FE, 43 F0 1 2 3. Oh, this is FE right here. Okay. I wish we got a call stack here. I don't know if we do. No, we don't. 4 4 3C. 4 4 3C. Yeah. Okay. So this is the return address. And if we go through this, I think we'll see that this gets written onto like here. So let's go and we'll set a breakpoint right after here. We're going to continue. We're going to type password. And yeah, we see that password gets written onto the stack. 443C. So we want to do 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. So yeah, so that's our 16 bytes. So we're going to do 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then we got to get the address of unlock. Unlock door right here. 4644. I think that this is basically all we have to do. We're going to reset. We're going to continue. We're going to get rid of that. We're going to continue. And we're going to do that, plus check that encoding. Finish. We're just going to continue. Door unlocked. Cool. Okay. So let's go for the solve. All right. Everyone follow what we did there with the little Stack Overflow. The password was being written like just onto the stack. And because of the way that the calling convention works, we can overwrite the return address with our unlock function's address. So when we return out of that function, even though we failed to type in the correct password, we still unlock the door. Let's see. Microcorruption. So that was Cusco. All right, there. Function accepts 30 characters even though at max 16 chars. Password is written directly onto the stack, but the stack only space created for 16 characters. This allows the return address written with the address of unlock door. The password check will fail, but after the function returns, the door will be unlocked. I think that it was unlock door is the. Let me just make sure that that's correct. Yeah, unlock door. Cool. So we can move on to Reykjavik. This one is also 20 points. I think the way that this works is it has like different revisions. So, like we're just working through all the revision 1 stuff right now, or revision 2 or whatever. Lock It All developers have implemented military-grade on-device encryption to keep the password secure. This lock is not attached to any hardware security module. So there's no HSM, but they're doing all the crypto in firmware. This is revision 2. They fired the engineers. All right. So we have some main stuff going on here. It looks like there's some address 4520. What's the password? All right, so that goes into R14, into R15, and then it moves F8 into R4. Shit. Sorry, the girlfriend is cleaning right now and just dumped a bunch of stuff. I don't know if anyone heard that. So F8 is in R14, and then what the fuck? So what I don't get is why it would move this into R14 and then R15, but then F8 goes into R14 and R15 gets overwritten like before enc is called. Like there's no point like where this is ever utilized as far as I can tell. And then 2400. What the fuck is going on? So it looks like it's, so 2400 isn't filled out yet. So it looks like it has code that's encrypted. I don't know, actually, is anyone here, if you can all read this on the stream, or if I should like increase the size here. Maybe I should just do it regardless. That's probably fine. So enc is 4486. There's probably some blob of like shit in here somewhere. Like just some blob of data. Oh, FF8. That's probably not it. So we're pushing R11, we're pushing R10, R9, R8. I think this is just to save those values. We're going to end up using them in this function. I don't know what CLR does. Let's see if we can find that. MSP 430 instruction set. Clear destination. So it just clears the value. Does it just set it to 0? These are status bits. It doesn't do anything. Unaffected. Emulated instructions. Okay. Doesn't even list that here. All right, well, we're just gonna go ahead and probably ignore that for right now because I don't know exactly what it does, but I don't know if it matters. So it moves R13, which maybe is 0, to 24/7C of 0. So I think that this is gonna just move whatever's in R13 with 0 to this address, and then it's gonna increment R13. And then it's going to compare 100 with what's in R13. Let's reset this and actually like jump through this. Step, 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 step. All right. So I think this is all of our encrypted data, probably. Maybe? What's our stack pointer? Our stack pointer is at, yeah, so this is some just initialized data. R13 has 0 in it. And 24/7C. 24/7, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C. Increment R13, it now has 1 in it. What's hex 100? Is that? It's 256. So we're gonna do this 256 times, I think. Jump not equal to 4490. All right. R13 has 1. 24/7C, offset of 1. So it's basically going to count us up to here. That is so strange. Let's set a breakpoint here then, and we're going to continue. So we've got basically every byte written into here. And then we're going to clear R13, which probably sets it back to 0. Yeah, so it sets it back to 0. Then we're going to move R13 into R11. So R11 is 0 now. Then whatever is at address R12, which is 24/7C. 7 0 1 2 3 4 5 6 7 8 9 A B C. So that's the first byte there. So it's gonna move the what's at R12, which is 0, into R8. R8 is 0, and it's going to move R8 into R10. R10 is now 0. We're going to add R10 and R13. R10 is 0, R13 is 0. So that's 0. And then we're going to AND F, which will be 0. And then move R10. 4472. So this data right here, so D8 or 8D is going to go into what is it? The address of 447. Is this code? 4472. It's 447. Into R12. Sorry, R10. So R10 has 0054. 4472. 54. So it moved the first byte into R10. And then 24/7C into R12. F E D C. So 0 into R12. Wait. Oh, we're down here. So I don't know what SXT is. Sign extend byte to word. Okay, so it just takes a 8-bit value and makes it 16. We need to go back to here. So R10 now, so it basically moved the 54 from here to here. We're going to add R10 to R13. 54 0. And FF with R13. Move R13 to R10. Then add 0 with R10. And the address of R10, 24D0. D0 to R9. Let's finish this. So now this is code right here. Did this get updated? I guess. 20i. 2400. Can we do disassembly arbitrarily? Reg, untrack track, read. So that's how you do it in GDB, but can you disassemble any arbitrary stuff? I guess not. So let's just jump. Where am I? I'm at 2400. Oh, do I need to get a disassembler to do this? Is there not like a... It looks like there's no way to do this within here. I guess we can dig out like a not ESP, an MSP 430 disassembler. Is there really no way to do this? Track bytes. Yeah. All right. Well. I'm gonna copy this. Data txt. That's not what I wanted. Yep. All right. This is gonna suck because I don't think I can. I don't want to do that. I want. Oh, fuck. So normally I would do like Control V, and I would go into like block mode, but I don't know. I can't do that really. Windows terminal vim. Yeah, this is what I want. I wonder if I can disable the, there's not even like options here. This is super frustrating. We're gonna have to do this like line by line. guess I could record a macro. And all these are missing. Wait, what the fuck? How did I cut off the first byte? It does cut it off. What the fuck? I don't know what it is about this terminal, but like it's just kind of wonky. Like the cursor is like not always in the right spot. I wonder if there's like a newer version of it that I can download. I don't even know how to tell like what version this is. Oops. All right. So we're good there. Basically just do that. And then we're just going to do a regex to replace with nothing. There we go. All right. Firmware.text. And then we can do xd pr firmware. Firmware.bin. All right. That looks correct, I think. 0b12. Yeah, all right. So we have our firmware. Let's see if we can get a MSP430 disassembler. Binary Ninja doesn't do it, does it? We can try this. Firmware.bin. Mount C users. J Rosner. Downloads. Let's check this out real quick, because there is a small possibility that this will just work. If I go to the where's the thing here? Give me like the settings, preferences. Yeah, there we go. Manage plugins. All right, MSP430. I don't know if it's good or not, but fuck it. I don't know if I have to restart this or not. I don't. Okay, cool. This will be at 2400, I think. Yeah, 2400 is where this is based. Standalone is fine. Open. List out of range. What? Unable to restore ARC ID mappings for MSP430. All right. So basically, this is garbage. Oh, we can try this one more time. Maybe I fucked something up when I was doing that, but I don't think I did. 2400 is the load address. Modify my review. I don't know, whatever the default value is. Yeah, I don't know. This is not helpful. Manage plugins. We're gonna get rid of this. This seems like it's not gonna work. Uninstall it. All right, come on. You can do it. You can uninstall it. All right. Great. So, let's find a different MSP430 disassembler. We might be able to use sudo apt install bin utils MSP430. The other thing we should look at is if there's a disassembler, which it seems like there isn't. Is there really no way to do this? That's not helpful. Yeah, let's see if we can use this. MSP430 obj dump. I kind of feel like this is gonna only work for ELF, but I don't know. No, that seems like that does it. Bin. It looks like B is not supported here. We can try. Disassemble. Yeah, the format's not recognized. So we're kind of shit out of luck with that. I have IDA, but not on this computer, and I don't have a Windows license for it. I mean, this is I mean, it seems like this. No one's complaining it doesn't work. Try this one more time. Maybe I do need to restart Binary Ninja. Like, there's. Oh, I gotta move it again. Manage plugins, MSP430. All right. So that's loaded. Predicted architecture, not detected. Okay. Invalid instruction length reported for address. What is it, like 1.5? I mean, we can cut it out. So it's 151 hex bytes in. So what is byte 337? $151. Like, why? I mean, I can count. Let's try to open firmware too. Count, see, users, download. Like, I don't understand exactly why it would fail like it is, but I mean, I mostly just. So it looks like it's usable. I mean, this looks like code. This looks like it's correct. We don't have function names or anything. I feel like there's supposed to be an easier way to do this, though. We shouldn't have to have like an external tool to, like. Oh, there is. That's fucking annoying. Okay. Yeah. Firmware.text. Disassemble. There we go. That's all of the code. But we don't get like addresses. Which kind of sucks. What's 4520? It's right there. Yeah, that kind of sucks. I wonder if we can do this and just click to the right spot. Oh yeah, we told... maybe not. I don't know. It seems like it's failing. Can we make function? Okay. Interesting. Okay, so let's go back. Discarded that. We're gonna do that. We're gonna set this at 2000. Current base. We did that. Now we want to interpret this as code. So like normally C would do that. It might just be transform. Make function. So P is procedure. Yeah, just give me the linear disassembly. I just want this. Also, just want my disassembly. Give me my linear disassembly. So it's confused again. So let's see. I don't know, this looks like garbage to me. This doesn't look like real code. This does look like real code. So 2464. We're missing stuff. Two, 4, 6. That's interesting. So it didn't read the full amount in. Oh, no, it does. It's 2400, not 2000. That's why. Okay. We fucked up. Try this one more time. SP430. And it's at 2400. Okay. Disassembly. Disassembly. All right. So this is int, I think. Maybe. Because it's calling, it's pushing 7F, which we know is the which we know is how you unlock it. I don't know what the fuck all this is, like, why this is failing like it is, but we're at least getting something that looks like it's correct here. This, I don't know. I mean, is there an int in here? There is. We can compare it. Move SP R14, push SR. Yeah, this looks just like that. Pop SR, so yeah. And there's a ret, and this is like, I don't want it to be a procedure, I just want it to be code. Like, make function. I just want you to treat it as code. I mean, I can hit P. We can turn it in to that, I guess. But let's go back to linear disassembly. Oh, that's interesting that, like, this is ASCII right here. That's really weird. What is that? 6973. 6854. This. Yeah, so that's ASCII code. So ASCII, so 73 49 65. I think our endiness is wrong. 73 6. Where does it start being meaningful? It's like right here, maybe. Because 41's A and 32 is, I think, space. A2. A0 or 0A. Let's try it going non-little endian and just seeing what we get out of this. it could just be byte oriented, which 7-3. Yeah, so this 49, 73, 49, 73. This is oh, no, that's why. It's too many times. 53, 65, 63, 75, 72, 65, 52, 69, 67, 68, 74, 3F. This is secure, right? I'm gonna guess that this is probably the password. Interesting. So that didn't work. So we found this. Wait, did that change on us? Oh, it's right here. A2, A0. That might be a coincidence, but this is not. So let's go back. Did we see references to... Like, this looks like garbage. Yeah, so this is an int function. One, two. What do the prologues look like? 0B12, 0412. BD9. I wonder if this is... No, that's probably not it. I mean, I guess we know what the things disassemble as. Move ret. I mean, does even decode the same? Push, push, move, add, move, jump. I guess it's resolving it. So like this is, I mean, yeah, I guess semantically it's the same, but it's not decoding the same. And push, push, call. Add 4 to the stack pointer. Move, jump. Push. Push. There. Add. Push 1F. Push, push, call. Add. Compare. That's all like ASCII. Not ASCII. Jump not 0. Call, add 2 to the stack pointer. Yeah, maybe. Add 20 to the stack pointer. Move SP, so pop R4, pop R11, ret. And does move 2 of the stack to 14, SR, move, swap by, maybe, I don't know what SWP is. Move, biz, call, okay. And so this should be a call. But like that's not real. Like this, let me turn the lights on also. So this is where things start to go off the rails. I mean, like this call doesn't seem like realistic. Like, I mean, this isn't even mapped into memory, as far as I can tell. And we got some invalid shit. I mean, like, some of it could be data, which, I don't know. So, I mean, I guess we could start stepping through this and just seeing what it does. And that might be the move. All right. I mean, and this is like the thing is like, this is also ASCII. I wonder if so we didn't decode this yet. I wonder if there's like meaningful data there. Seven, 7, 6, 8. 6, 1, 7, 4. 27, 73. So this is what's the password. 71, 73, 73, 77, 6F, 72, 64, 64, 3F. Yeah. So this will end up decoding as what's the password. And then this here decodes as this is secure, right? I mean, I guess we just do this. Can we set it here or not? No, we can't. Okay. Continue. Finish. Now, if I step, will it highlight it in here? It doesn't. Of course, it doesn't. Yeah. Okay. So push R11. Push R4. So the stack pointer gets. So we're. What's the stack pointer gonna? 43DA. Something like in here somewhere. So 4520. Okay, so yeah, it's moving 4520, which has a string of what's the password. We're gonna jump forward 10 instructions. We're at 2420, 4520, or 2420. Wait, did I fuck something up here? Nope, we're good, okay. We're gonna do that. R15. What's R15? 77? Inc R11. 4521. Where the fuck are we now? So we're at 2418. Push 0. Call 2464. I kind of think this is interrupt, but I'm not sure. Yeah, it's definitely interrupt. What? 10 is trap interrupt, okay. So yeah, it's literally printing the characters. We're at 2416. We're at 24.1a. 24.1a. So we pushed R15. What's in R15? Is hex 3F. Oh. Right, okay. So then we're going to add 4 to the stack pointer. We're at 2420 now. We're going to jump, not 0, which fails. So we're going to push hex A. We're at 2426. So we're pushing hex A, which is 10. Is that 10 bytes? The 3, 4, 5, 6, 7, 8. Okay, so I don't know what this is yet. Add hex. Okay. I'm just gonna do that. Right. So we're at 2444. 24. Okay. So that is correct. B7. What's it, R4? R4 is so 43F. So 43DA. 43D. Okay. B7A0. So that's all we need is B7A9. Continue. Continue. I wonder if we can set a breakpoint here. I don't know if this will resolve, but all right, continue. B7A9 step. Twenty-four 5A. Wait, what? B7A9. Do I need to put it in differently? Okay, that's it. We did it. All right, so solve. B7A9. Wait, what? Oh, did I put it in? A9, B7. All right, we got it. A9, B7. One sec. Give me 1 second. I'm gonna let the dog in. I think he's gonna want some attention. Oso, you wanna come in here? Yeah, you wanna lay down? All right. So this was Reykjavik. Reykjavik. All right. I'm so, like, I'm genuinely so curious, like, what was, like, why the strings were there, but I mean, whatever. So, this firmware uses on-chip encryption software to decrypt it and jump into it. We can dump the decrypted let's just get this written up real quick. In ink. Values. Memory. This can disassembled. The relevant code. I was gonna copy address, but I think it's just Shift Control A. Yep. Solving this is at B789 to memory. Input. This value. All right. I don't think I've ever solved this one before. Let's see. Let me see where the dog is, make sure he's okay. You want to come in here? What's up, Mike? Going through this game. Yeah, I'll probably play a little bit later. I'm gonna play this a little bit longer, and then I'm gonna take the dog out for a walk, and get some food, and then probably down. Hey, you want some attention? Yeah, okay. You want to lay down also? Let's check out Whitehorse and see what is it. It's 50 points. Johannesburg is 20. I don't know what this is. Let's see how difficult this is going to be if we want to go with something easier. So this is an HSM2. We haven't done these yet. Let's see if there is a different one that we want to run. Hey, can I stop petting you now? You want to lay down? Oh, you want more? Johannesburg is only 20. We can see what's in here. I don't know if this is HSM or not. It is an HSM. Passwords that are too long are rejected. I guess we could try this. So the Locket Pro B04 is the first of a new series of locks. It's controlled by MSU430s, most advanced, blah, blah, blah. Oh. Yeah? Do you want to go outside? Is that what you're trying to tell me? Alright. I think we're going to have to cut this short. I think we have to go on a walk. But maybe tomorrow I'll do some more. Made some good progress today. Can you hold on a little bit longer, or do you need to go right now? You want to sit down? See if we can solve this real quick before I have to leave, and then go on from there. I can't. If it's only 20 points, I can't imagine it's that difficult. It looks like there's a stir copy, which probably means that's where the vulnerability is. It's probably going to be another Stack Overflow. Do you really want to go? All right. Yeah? All right. All right, we'll wrap it up. Sorry about that. I think we gotta take him out. Anyway, we'll do some more tomorrow. Maybe I think I have some afternoon time, and we can see how far we can get on it. Good night, everyone.